Hey everyone, welcome back to Everything is Relative. Today we're going to be looking at a question 2 from a paper 5 from the May-June exam of 2023. That's the summer exam series 2023, and this is from question paper 5, variant 1. And this is for Cambridge A-Level Physics with the subject code 9702. Now, in a previous video, I did question 1 from this paper, and I will leave a link in the description of this video for you to find this paper and work through it before you attempt to look at the mark scheme or before you attempt to look at this video and have an idea of how to answer this question. So I think this was an interesting question and one that was, I think, sufficiently challenging. And if you've already done this paper, then you know this question is about capacitors. So we are told that a student investigates the discharge of capacitors in the circuit that is shown, and the capacitors have capacitances CP and CQ. So there are two capacitors. And the student closes the switch to charge the capacitors and then records the maximum voltage V0 on the voltmeter. The switch is opened and a stopwatch is started. The capacitor is discharged through the resistor and the reading on the voltmeter decreases. When the reading on the voltmeter is V, the time t is recorded. The discharge of the capacitors is repeated and the mean time t is calculated. The experiment is repeated for different values of Cp and Cq. And for each combination of Cp and Cq, the combined capacitance C is calculated. It is suggested that C and T are related by the equation the natural log of V over V0 is minus T over CR, where R is the resistance of the resistor. Now, in question 2 of paper 5, you never really need to be able to derive the expressions for the mathematics. You'll usually be given the equation that's going to describe what's happening. And unlike question 1 where you design the experiment, in question 2 the experiment will be given, data will be given, and you have to analyze and work with that data. And if we are told that R is the resistance of the resistor here, and given the suggested relationship, we're obviously going to have to plot something against something at some point. And question A says a graph is plotted of T on the y-axis against C on the x-axis. Determine an expression for the gradient. So I need to linearize this equation so that I can find a gradient and a y-intercept. So what I'm going to do is I'm going to plot T on the y-axis. So I'm going to put the thing that's going to be on the y-axis on the left-hand side of the equation. And so with a little bit of mathematics, I see T is equal to minus RC times the log of V by V0. Now, this you can see is in a linearized form. And so if I were to plot T on the y-axis and then plot C on the x-axis, then everything in front of the C would be my gradient. And there isn't a y-intercept, so this graph should ideally pass through the origin. So then I would specifically or explicitly state that my gradient would be minus R times the natural log of the voltage after time TV over the maximum voltage V0. And I can leave it in that form. So yes, we can remove the minus sign, but there isn't really a need for us to do that. If you wanted to, you could write this as R times the log of V0 over V. So you just flip the fraction in the log, but unnecessary. So the gradient is minus R log V over V0. And so we obviously know we're going to move on to the table. Now the table can be quite complicated. We are given values of Cp, Cq, and T, where T is the measured time for the discharge to happen. And we are told that the relationship between C, Cp, and Cq is given by C is Cp, Cq over Cp plus Cq. Now again, this is a relationship you would know, but they would usually provide you with this relationship. And again, it's not testing your knowledge of the physics, it's testing your knowledge of, well, how well you work in the lab, your lab skills. So we are asked to calculate and record values of C, with units 10 to the minus 4 farads, and T in seconds in the table, and include the uncertainties, the absolute uncertainties in T only. Okay, so to find the capacitance, I'm simply just going to have to use this equation. Take the value for Cp, multiplied by Cq, divided by the sum of Cp and Cq. And I need to make sure I keep the significant figures the same. So if I do that for the first two values, 2.2 times 1.5 all multiplied by 10 to the minus 4, divided by 2.2 plus 1.5 all times 10 to the minus 4, I get 0.89 times 10 to the minus 4. Be very wary of the power of 10. And so I've kept that to two significant figures since I've used two significant figures in the calculation. And for the next value, I'm going to keep consistent with the number of significant figures even though my number of decimal places is not consistent. I get 1.3, and then I get 1.6 for the third row, 1.0. Notice how I didn't write that as simply 1. Two significant figures is 1.0, 1.2, and the last value is 2.1. Now that's not too difficult. The equation is given, you simply put it into a calculator and make sure you do it accurately to two significant figures. Now the time is a bit more complicated because I need to find an uncertainty, an absolute uncertainty in the time. Now I don't actually know what the uncertainty is in measuring the stopwatch. I mean, people like to estimate 0.2 seconds for human reaction time, but again, that's not very accurate. Reaction time changes and it's not accurately known for each individual. How I would find the time is to find the average of the two times. T1 plus T2, first column plus second column divided by 2. And you can see the times vary quite a bit, quite significantly. Again, this is because we're using a stopwatch. We aren't using some timer automated method. And what you remember from measurements is that if I wanted to find the absolute uncertainty for a range of readings that I took, I can take half the range of those values. So what does half the range mean? It means I take the bigger value minus the smaller value, since I only have two values in this case. So the range is only, well, for any set of values will be biggest minus smallest divided by 2. That's why I got the absolute value signs, because it's the modulus of the one time minus the other divided by 2, and that's going to be half the range of values. I only have 2, so the range is just the distance between those two values. And what I find is that the average time, if I take 12.9 plus 14.5 and you divide it by 2, if I stick to this consistency, I have 13.7 seconds. That's my average time. But now I need to find the uncertainty. So if I use my second formula for delta t, the absolute uncertainty, what I find is this is 0.8 seconds. 13.7 plus 0.8 gives me 14.5. 13.7 minus 0.8 gives me 12.9. I've calculated the average value basically, and plus or minus the distance to the higher and lower values. And I'm keeping the same number of decimal points in the uncertainty as I have in the measured value. Now if I do this for the rest of the rows in the table, I have 20.4 plus or minus 0.7, and you'll notice something strange happening here. And then I have 24.3 plus or minus 0.6. For the fourth row, I have 16.1 seconds plus or minus 0.8. 18.3 for the fifth row, plus or minus 0.7. And for the final row, 31.5 plus or minus 0.6 seconds. Now it might look like the data is actually fluctuating, but if you look at the column for C, the values are not necessarily in any sort of order. They're randomly distributed. But if we were to order them, you'd see that as the time increases, the uncertainty in the time actually decreases, which kind of makes sense. If you use a very large time, you're less likely to make an error with reading the stopwatch. This is why you try to keep times as large as possible when you do things like oscillations and so on. And so I should have all of these values as they are stated here, and the number of decimal points in the uncertainty should match the decimal points in the measured value. So now that I've completed my table, I'm told, as I always am in question 2 of paper 5, to plot a graph, and I'm usually told what to plot where. So it tells me to plot a graph of t against c and include error bars for t. Now, when I go onto the graph sheet, what I won't find is the points plotted for me. Unlucky for you, I've pre-plotted the points, but you will find that the axes have been labeled and they've been scaled. So this makes your job a lot easier, but it also means that every one of your graphs have to look very similar to the next person's. And so you have to make very certain that where you're plotting your points is the correct point. You aren't allowed to shift points because you were too lazy to check, etc. You have to make sure your points are where they should be. So the first point I'm going to plot is, again, C is on the x-axis, so 0.89. Do not plot CP or CQ. 0.89 is going to be on the x-axis. The units on the x-axis were already 10 to the minus 4 farads. And on the y-axis, I'm going to plot 13.7. So where I've put my x is 0.89 and 13.7. But wait, I need to add error bars as well. Now we said we think the point is 13.7, but it could be 12.9, but it also could be 14.5. So you actually didn't need your uncertainties here. You could simply use the values for t's, for the little t's, and you could have just plotted those points on the graph, and you would have gotten those error bars, whichever works for you. But you had to make sure your error bars were the right length. So my lower point here is actually 0.89 and 12.9, and my upper point was, they all have the same x coordinate because they all lie on the same vertical line, 0.89 and 14.5. And the uppermost point is equidistant from the central point as the lowest point is. And that's how the error bar should look. It should be symmetrical about the point that you plotted. Now, I've drawn the error bars and the points quite thickly. You'll draw it a lot more thin with your pencil, sharp. But I've just drawn it this way so that you can actually physically see what I've drawn. I'm just going to erase these. I don't want to have too much of these on the graph. You shouldn't be labeling all the points. It would get a bit messy and monotonous. But if I do this for every single point, I'll notice as well that as I get up with values of time, I get smaller error bars. But the error bars still need to be symmetrical about the central point. And you might notice that my error bars might be slightly here or there. It's difficult. It would be a lot easier, again, like I say, with a pencil on paper, on flat paper, to plot these points. But anyway, once I have these points plotted, I'm now able to, well, actually I get 2 marks for plotting the points, 1 for the points actually, and 1 for the correct error bars. So there's very little room for error. There's 1 here for plotting the points, and there's 1 for the error bar. So for 2 marks, you have to make sure that you are precise as ever, as you should be when you're doing anything in the lab. We now have to draw the straight line of best fit and the worst acceptable line on the graph, and we have to label both lines, something we shouldn't forget to do. So unlike what you would get in your exam, there will not be a magic set of points plotted for you, and it definitely wouldn't be a magic graph that's pre-drawn like there is for me. But for now, that's a you problem. But anyway, when you have your graph, your line of best fit plotted, again, remember your line of best fit should balance the number of points you have. If you look at my line of best fit, it does pass through a few of the points. But on balance, if you look at the point right at the top, it's below the line. My second point at the bottom here is above the line. If I balance it out, I would say on average, there's as much of the points above the line as they are below the line. They don't have to be an equal number of points above and below the line, but on balance, it should be the best line of best fit that you have. And once I plot the line of best fit, I have to plot the worst acceptable line. So this is going to be the steepest or shallowest line that is going to pass through all of the error bars. Usually what we do is we draw a line from the bottom of the top error bar to the top of the bottom error bar, or vice versa. So in this case, what I've done is I've drawn it from the bottom of my of the error bar at the point at the top through to the top of the error bar of the point at the bottom. And why I've done this is so that the blue dotted line, which I have for the worst acceptable line, is passing through all the error bars. If it's passing through all the error bars, then it's either the steepest or shallowest line that can pass through all the error bars. And in this case, it's going to be the steepest possible line that we can draw through the error bars. So it's essentially like a visual representation of your errors in a way. And they did ask me to label it. So I'm going to say worst acceptable line, because I'm too lazy to write acceptable. And then the black line, you'd probably draw this, you will definitely draw this both in pencil. Maybe you can draw one as a dotted line, but it's fine to draw both as solid lines. Just make sure you label them. And then the black line for me is the best fit line. Regular best fit line like you would do in paper 3. And so I have my best fit line and my worst acceptable line. And I have to be very careful that I draw those to the best of my ability. Because how I plot them will determine whether or not I'll score the mark for the line of best fit. And so precision and accuracy and those sorts of things are as important as they'll always be in a lab. Now I'm asked to find the gradient of the line of best fit and include the absolute uncertainty in the answer. So I'm not going to go and show you the points that I actually chose, but I trust in your ability to find gradients of lines. Well, I hope that you have the ability to find gradients, but I always like labeling the work that I'm doing. So I'm going to say best fit gradient equals, so we know what we're talking about when we're doing calculations, and I've used the points 30 minus 22. Remember, gradient is delta y by delta x, so I've taken two of the points on the y-axis, subtracted them, then taken the two corresponding x coordinates and subtracted them to find the gradient. 1.975 minus 1.435. And I multiply this by 10 to the minus 4. Now again, I mean, mathematically, you don't really need the 10 to the minus 4 because it's just a scale factor in a sense, but I prefer to have it there because I know that it means something physically. It's some physical quantity. So I prefer to have it there so it makes my job a little easier later on when I have to use this gradient to find some physical quantity. So I get 1.48 times 10 to the power 5 seconds per farad. Again, you don't need a unit, but it's good to have a unit so you can visualize what the gradient of the graph is giving you. It's giving you something that's measured in seconds per farad, whatever that may be. Doesn't really make our life that much easier. What about the worst acceptable line? Again, you have to show your calculation of the gradient, especially because if you get it wrong, you won't be given marks for just writing a wrong gradient down. And what you should usually find in paper 5 question 2 is that your gradients will not differ by too much. It won't be a massive fractional uncertainty. It shouldn't be a massive fractional uncertainty. And again, these points should be from your graph. They should not be points that are in your table but are not on the line themselves, and also should be separated by a fair distance. And what I get is 1.36 times 10 to the power 5 seconds per farad. So I can see that my two gradients are not far off, not too far off at least. Not powers of 10 difference in order of magnitude. How do I find now the uncertainty in the gradient? I found the gradient of the best fit line, which is what I wanted. But the uncertainty, which for lack of a better name we'll call delta gradient, is the difference in the two gradients. 1.48 minus 1.36 times 10 to the power 5. That's why I said that the worst acceptable line is sort of a visual representation of the error in the experiment, because it gives you the difference in the gradients, gives you the actual uncertainty. And I'll keep the power of 10 the same, 0.12 times 10 to the power 5 seconds per farad. It's not a massive difference. Well, it doesn't seem like a massive difference now. So my gradient is the best fit gradient, it's 1.48, plus or minus this difference, 0.12. Don't forget, multiplied by 10 to the power 5. And the units, although optional here, I would just suggest it, just for convenience sake for following questions. So that's how you find your gradient of the best fit line, and then the uncertainty. You find the gradient of the worst acceptable line, subtract the two, and there's your absolute uncertainty in the gradient. Now, the last question, or the last page rather, usually has all your analysis, where you take the data and you put it through various calculations and you find uncertainties and errors and so on. Now we're told that the values of V0 and V are 4.8 plus or minus 0.1 and 2.4 plus or minus 0.1, and both in volts. We want to calculate the log of V over V0 and include the absolute uncertainty in the log of V over V0. Okay, so this is quite a bit of work for 1 mark here. So I need to find the natural log, or ln if I could, the ln of 2.4 over 4.8, which is essentially the log of a half, the natural log of a half. And this is equal to minus 0.69. Now the uncertainty, how am I going to find the uncertainty for the log? So the uncertainty in log of V over V0 is, what I'm going to take is, I'm going to do the range thing again I did for the time. I'm going to take the biggest number minus the smallest number in the range of log V over V0, and I'm going to divide that range by 2. So I'm going to take log of the bigger fraction. I'm going to use an absolute value sign because I just want the magnitude of the uncertainty. The biggest fraction, 2.5 over 4.7. That's going to give me the biggest fraction. 2.5 is 2.4 plus 1, and 4.7 is 4.8 minus, well, 0.1. And so what this does give me is the biggest fraction. And I'm going to subtract the log of the smallest fraction, 2.3, which is 2.4 minus 0.1, over 4.9. 4.8 plus 0.1. I'm going to take half this range like I did for the time. And if I do this, what I get is 0.06. So instead of confusing yourself with log laws, etc., this is a simple way to find the uncertainty without having to do any mathematical expressions for the absolute uncertainties for logs and so on. And what I get is minus 0.69 plus or minus 0.06. So I just simply manipulated the uncertainties in the values for V0 and V to find the uncertainty for the log of V over V0. And so this is my value for the log of V over V0. Again, this does not have units. The log of anything is just a value, just a number, dimensionless. So there wouldn't be a unit of measurement here. Just be very careful of that. We are now told to use our answers to A, C3, and D to determine the value of R and include an appropriate unit. Okay, so there's quite a lot of things we need to do. Well, what we can do is immediately say that the gradient, which we already mentioned before, is minus R times the log. I'm just going to say log from now, but you know I mean natural log. The log of V over V0. Which means that with some fancy mathematics, we get R to be minus the gradient divided by the log of V over V0. So I can find R, and this is minus 1.48, because there's a minus sign there, And the gradient I'm just going to take from the previous question where I calculated the gradient, minus 1.48 times 10 to the power 5 divided by the log of v over v naught. I can just take it from the question above, minus 0.69. And I use the SI units for everything thus far, so I can actually just write down my answer as 2.14 times 10 to the power 5 ohms. I know it's going to be ohms because, like I said, I use the correct powers of 10 and the correct units, and I can just write I know what the unit of measurement for resistance is. It's an ohm. If I want, I can write seconds per farad as well, but you'll see that just becomes an ohm again. And they did only ask me to calculate R, but I'm also going to calculate the absolute uncertainty in R, because I do have a feeling they're going to ask me for that. Actually, I have more than a feeling. I can see it just below. So I'm going to calculate the absolute uncertainty, which makes the next question a lot easier. The absolute uncertainty, delta R. Now R is gradient over the log of something. So R is a quotient. It's the one number divided by another. When we're having one number divided by another, that gives us a quantity, then the uncertainty in that quantity must be calculated as its fractional uncertainty. So delta R over R is delta gradient over gradient plus delta log of V over V naught over log of V over V naught. And so this gets a bit messy, but basically this would be the fractional uncertainty in the gradient plus, I guess I just write it so that it's visible, delta log of V over V naught divided by the log of V over V naught, which is fine because we actually already calculated that. And we multiply this all by R. And so putting in the numbers, you see it becomes a lot less messy. The uncertainty in the gradient was 0.12 divided by the gradient, which is 1.48, plus, even though there's a minus sign, we still have to add because we are trying to maximize the uncertainty. The uncertainty is greater when we make more measurements. Plus the uncertainty in log of V over V naught, which we've calculated already, 0.06, divided by the actual value of log of V over V naught, 0.69, multiplied by the value of R, which we just calculated, 2.14 times 10 to the power 5 ohms, which gives us 0.36 times 10 to the power 5 ohms. Notice how I'm keeping the power of 10 the same. And that's so I can write it nice and neatly. The final resistance will be 2.1 plus or minus 0.4 multiplied. It's going to be a very high resistance. And this is going to be multiplied by 10 to the power 5 ohms. So we've calculated the value of R. We will also calculate the absolute uncertainty in R, which we didn't need to, but will be helpful. And we've given the appropriate unit. So we've stuck with ohms, which I like to do. I like to stick with the quantities of the units that I know. And I get 2.1 times 10 to the power 5 ohms plus or minus 0.4 times 10 to the power 5 ohms. So the actual number 0.4 is not big, doesn't seem big, but if you think of it in comparison to 2.1, how much of an error is that I'm carrying forward? Well, the percentage uncertainty in R is the fractional uncertainty delta R by R times 100. So now all the working I did above becomes clear. That's 0.4 over 2.1. I don't need the powers of 10 because they'll cancel off anyway, times 100, and I get 19. There's a 19% uncertainty in my value of the resistance. So even though I had very small uncertainties in my initial table, these compounded with the numbers of calculations I've done ended up being 19%. I mean, in most labs, 19% will be unacceptable to use for any conclusion to be made. And in part F, we are told that the experiment is repeated, and we want to determine the value of C that gives a value of t of 60 seconds including the absolute uncertainty in the answer. So we are given a value of t with certainty. We're going to make the assumption that that t value is certain, 60.0 seconds. There's no uncertainty in that. And then we want to find the value of c that will give us this time t. And using the expressions we already have, the value of c is minus t over r times the log of v over v naught. So the mathematics will always be there. Like I say, it's all about you rearranging it. And this is minus, now the time is given exactly as 60 seconds. We're not going to include uncertainty for that. Divided by the resistance 2.1 times 10 to the power 5 ohms times the log of v over v naught, which we already calculated to be minus 0.69. There had to be a negative here somewhere to give us a positive capacitance. And what we get is 4.1 times 10 to the minus 4 farads. Hey, this is quite good, because if we go back to our table, it will match up. For the time to be about 60 seconds, if we look as the time increases, the value for C is going up as well. And so at about 60 seconds, you'd expect the value for the capacitance C to be somewhere around 4. And the power of 10 is correct also, 10 to the minus 4 farads. So it could mean that whatever we've done so far is fine. We've been working with values that are roughly in the ballpark of being correct. But we also need the uncertainty in C. Delta C is, now if I look at this equation, and T is a certain thing, then it's a certain thing divided by two uncertain things. So delta C will be again, it must be a fractional uncertainty. The fractional uncertainty in R plus the fractional uncertainty in the log of v over v naught. It's messy to write, but not complicated. And all of this multiplied by the calculated value of the capacitance C. And delta R by R is the fractional uncertainty in the resistance, which we already know is 19%. That's 0.19. Plus the fractional uncertainty in log of v over v naught. Again, 0.06 divided by 0.69. All of this multiplied by the value we calculated above, 4.1 times 10 to the minus 4 farads. And we get 1.14 times 10 to the minus 4 farads. So actually quite a significant variance in what the capacitance could be. So 4.1 plus or minus 1.1 times 10 to the minus 4 farads. That's 25% of uncertainty. That's quite significant. And you can see we take these small uncertainties, but as you do more calculation with something that's even slightly uncertain, you end up with answers that become more and more uncertain. So you always need to try and limit your use of uncertain values or make your uncertain values more certain, which is what you do in question 1. But this is the structure of question 2 for paper 5. It always will be, but you have to make sure you're comfortable with uncertainties and errors and significant figures, and how to calculate uncertainties for different equations, how to linearize those equations, and things on those of those sorts. I hope this video was helpful. If it was, please leave a like, subscribe to the channel if you haven't already, leave a comment if there's anything else you want me to do before the end of the exams. I will be moving on to some AS content before your paper 2 and paper 1. But from me, Mr. K, that's all for now. I'll see you again next time on Everything is Relative.